Hi and hello everyone. So let's continue with lesson 15 on subtopic 12.2, which is thermal expansion. So in this subtopic, you must know how to define coefficient of linear, area, and volume thermal expansion. Other than that, you must know how to solve problems related to the thermal expansion of linear, area, and volume, include expansion of liquid in a container. Alright, so these are all the equations that we will find in this subtopic. Alright, the definition of thermal expansion is defined as the change in dimensions of a body accompanying a change in temperature. Alright, so there are three types of thermal expansion. The first one is linear expansion. Alright, second is area expansion, and the third one is volume expansion. For your information, in solid, all types of thermal expansion, including linear, area, and volume expansion are occur. But in liquid and gas, only volume expansion is occur. So, at the same temperature, the gas expands greater than liquid and solid. Linear expansion. As we know, many solid objects will expand when heated. In this example, let's say we have a thin rod of initial length of L0 at temperature T0. What happens when we bring a candle very close to this solid rod in order to heat up the rod? Okay, so the thin rod will expand outward along a linear axis, and the distance by which the rod expands is given by delta L. Alright, where delta L is the change in length. Okay, delta L is equal to L final minus L initial of the rod. You can see the comparison of the length. Okay, based on the diagram, the length of the final length is longer compared to the initial length. Okay, so that means the object is expanding when heated. So now, given that the change in length delta L is equal to alpha L0 delta T. By using this equation, we can calculate what is the change in length when there is a change in temperature of delta T, where delta T is the change in temperature, alpha is the coefficient of linear expansion. For your information, coefficient of linear expansion alpha depends on the type of the material. For example, when we have a steel rod or the copper rod, these two materials have different values of alpha. So, when we calculate delta L for different material, there is a different value of the change in length when the object is expanding. Alright, so let's move to the next slide. Okay, now let's rearrange the equation of delta L. Okay, when we rearrange the equation, okay, you can see here alpha is equal to delta L over L0 delta T. Alright, so the definition of coefficient of linear expansion can be defined as the change in length, where this is the change in length of a solid, delta L, per unit length. Alright, so this is the change of length of a solid per unit length L0. So this is the length, okay, per unit rise of change in temperature delta L. Okay, so based on this equation, we can find the final length of the rod after heated. Alright, so how to calculate the final length? So, here is the change of the length delta L equal to L minus L0, where L is equal to delta L plus L0, and we simplify the equation. Then finally, okay, we got the new equation is L equal to, this L is the final length, is equal to L0 alpha delta T plus 1. Okay. So for many materials, the linear dimension changes according to both equation above. Okay, so we can calculate delta L, the change of the length, by using this equation. And we can use this equation in order to calculate the final length. Okay, after we simplify the equation. Okay, so L could be the length of a rod, or L could be the side length of a square plate, or the diameter of a hole. For example, the diameter, also the radius of a hole, where the radius is diameter divided 2. Okay, next. Okay, look at this example. Let's say we have a metal washer is heated. What happened? All dimensions, including the radius of the hole, will increase. Okay, so given that R1 is the inner radius, while R2 is the outer radius. Okay, so after heated, what happened? There is a change in the radius R1 and also R2 by delta R1. You can see here that the inner radius is increasing by delta R1, and the outer radius is also increasing by delta R2. Means that the final, let's say R1 final, is bigger than R1 initial, where the radius for the outer radius R2 final must be bigger than R2 initial, because the radius is expanding. Okay, now we will discuss about area expansion, where this type of expansion is involving the expansion of a surface area of an object. Let's say we have a plate where the initial area of the plate is A0 and at temperature of T0, where T0 is the initial temperature. So when the plate is heated to a new uniform temperature T, and we consider T is the final temperature, what happened to the plate? The plate will expand by delta A, where delta A is the change in area. Okay, so based on this experiment, we will get the change in area delta A is directly proportional to the initial area. Okay, and the change in area delta A also directly proportional to the change in temperature delta T. Okay, where delta A is the A final, you can write here as A final minus A0 A initial. Okay, and delta T is the change in temperature, so T final minus T initial, where B is the coefficient of area expansion. Okay, so we will use this equation, delta A equal to beta A0 delta T, in order to calculate the change in area when there is an expansion of area of the object. Alright, let's move to the next part. Okay, delta A is equal to beta A0 delta T. When we rearrange this equation, we will get beta is equal to delta A over A0 delta T, where beta is the coefficient of area expansion, where the coefficient of area expansion is defined as the change in area delta A, of a solid surface per unit area, per unit area A0, per unit rise in temperature delta T. Let's say we put it this one. Delta T is the rise in temperature. So the area of the surface of object at temperature T, or the final area A, at temperature T, can be written as A is equal to A0 1 plus beta delta T. So let's say we have delta A is equal to beta A naught delta T. So delta A is A final minus A initial equal to beta A naught delta T. So now we bring A naught to the other side. So A is equal to beta A naught delta T plus A naught. Okay, so when we factorize this equation, then you will get the new. Okay, actually this is the same equation. Okay, but when we factorize A naught, then we can write the equation as A equal to A naught 1 plus beta delta T. Okay, so for isotropic material, where the definition of the isotropic material or the isotropic solid is, it's actually a solid that have the same or identical properties in all direction, such as density. So for this type of material, we can consider the area expansion is uniform. Okay, the area expansion is uniform in all direction. So we can write the relationship between alpha and beta as beta is equal to 2 alpha. Okay, now this is about volume expansion. Okay, so for your information, when a substance that includes solids, liquids, and gases will undergo a change in temperature, it either expand or contract depending on whether or not the temperature decrease or increase. So in this case, we consider the temperature is increasing. So there is a volume expansion. Alright, so let's say we have a metal cube where the side length is L0, where the L0 is the initial length here. Okay, and this metal cube is heated, and what happened? It expanding uniformly. Okay, from the experiment, we get delta V is directly proportional to V naught, and delta V also directly proportional to delta T. Means that when the delta T is bigger, then delta V also bigger. Okay, delta V is the change in volume, delta T is the change in temperature. Okay, so now you can see based on this equation, the change in volume is depends on the change in temperature and also depends on the initial volume. Alright, and we have new coefficient here, and we call it as coefficient of volume expansion, where the symbol is gamma, where gamma is equal to delta V over V naught delta T. Okay, so based on this equation, the coefficient of volume expansion can be defined as the change in volume delta V of a solid per unit volume V naught per unit rise in temperature delta T. Okay, based on the equation of change in volume delta V is equal to gamma V naught delta T, we can also write the equation in terms of V is equal to V naught 1 plus gamma delta T. Okay, so now delta V is equal to V final minus V initial equal to gamma V naught delta T. Okay, so we can bring these terms to the other side. So V is equal to gamma V naught delta T plus V naught. Now we can factorize this equation. Then finally we can write V is equal to V naught 1 plus alpha delta T. Okay, so this equation is actually come from this derivation. Alright, same goes to the area expansion. For isotropic material, the volume expansion is uniform in all direction. Thus, we can write the relationship between alpha and gamma, where gamma, the coefficient of volume expansion, is triple the coefficient of linear expansion. Okay? Remember, for beta, the coefficient of area expansion is twice the coefficient of linear expansion. So this is very important, okay, because we will use this equation to solve problems in this subtopic. Okay, so before we finish, I want to highlight one thing. So when you read the question about linear expansion or area expansion or volume expansion, okay, please read the question carefully, especially for area expansion and volume expansion. If the question give you, okay, let's say the question is about volume expansion, but the question just give you the coefficient of linear expansion alpha. Oh, please be careful. You need to calculate the coefficient of volume expansion first in order to use delta V equal to gamma V naught delta T equation. Okay, how to calculate gamma? So remember this, where gamma is equal to 3 times alpha. So when the question gives you the value of alpha, which is coefficient of linear expansion, okay, please make sure you calculate first what is the coefficient of volume expansion in order to calculate the change in volume, for example. Okay, so that's all from me. So next week, you will continue chapter 13. Bye!